Welcome back, ladies and gentlemen. So we begin with the post-lunch session of tutorials. We have with us Professor Shankar Kumar Selvaraj. May we greet him with a big round of applause. So a very warm welcome to you. So Professor Shankar Kumar Selvaraj is in the Center of Nanoscience and Engineering Department in IISc Bangalore. He is also chair of Nano Fabrication Center at IISc. He will be giving us an introduction to the semiconductor technology. He secured his PhD from Ghent University, Belgium. He has to his credit 10 patents, and several of his articles have been published in international journals and magazines. He is a recipient of the DST-CERB Early Career Research Award, as well as Vishweshwaraya Young Faculty Research Fellowship Award from the Ministry of Electronics and Information Technology. So once again, warm welcome to you, sir, and over to you now.
All right, thank you. Can you all hear me at the back? All right, good, thank you. First of all, thanks to Professor Anil and the organizers of this Bangalore, India Nano for inviting me to give this tutorial talk. It's not a research talk, okay? It's a tutorial talk, so what it means is you're supposed to learn something, right? Not just hear something, right? So how many of you are aware of this thing called semiconductor technology or semiconductors? So all of you must have heard of semiconductors. So what is the difference between semiconductor technology, and so on, right? So there are some details in that, right? So that's what we will do, and why semiconductor technology in recent times, right? So this is the reason, right? So whatever you take around you, it has semiconductor in it, all right? So these days, even your toys that you buy for your kids or to gift to somebody, or even pens, right? So these days, you know, the pen is something that doesn't require any semiconductors, right? It's just pure mechanics that works on this, you know, simple writing ball pens. But now it also has semiconductors. Do you know why? Have you found semiconductors in a writing pen? Any of you? Huh? No? That's strange. I was actually going to bring something, but I then forgot. I had a pen that has a semiconductor in it. You know what? So you want to make the pen more exciting. It's just a boring thing to do, right? But what they have now put is, you know, an LED inside the pen that you can write your name and it will flash your name, right, when you switch it on and off, right? These kind of click pens. So people are trying ways to put semiconductors in everything, all right? So that means there is a demand for the semiconductors is increasing, right? So whether you like it or not, right, whether it is useful or not, like your iPhones and all your requirements or your apps and so on, the thousands of apps that you have, only 2 or 3 that you regularly use, the rest are useless, right, of similar kind. But what that has brought us to is this, right? So as a country, we have to look at this holistically. So semiconductor technology, why it is relevant now? So if you look at the numbers, it looks like it is going to be the new oil, all right? So oil was considered to be one of the most strategic resource, right? And some of us have lived through ages where there was Middle East conflict and suddenly there is a, you know, a rationing of your petrol and diesel, right? Right now we have ways to tackle that, but then it becomes a strategic resource. And similarly, the moment you start using semiconductors everywhere, it becomes a strategic resource. If somebody, you know, switches off the semiconductor pipeline, then you are going to suffer because your ecosystem is built around it. How big that is, right? So this is data from just 2023, right? So 2023 data tells us that that's the amount of money that we have spent importing electronics. Okay, so we have a very small, you know, industry that works on electronics, but not on semiconductors. If we put all together, 6.2 trillion, you know, Indian rupees, right? So if you convert that, it's going to be 75 billion. I was just, you know, flashed the news The MOS was giving a press conference, and the projection for 2030 is 100 billion. These numbers are going to increase, right? But if you don't do anything about it, and if you are just going to be a customer of electronics or semiconductors, that's not a good model. And why we are excited in the community is about this. So the country has realized that we need this, all right? So there is this Indian Semiconductor Mission program that's very active, and already we know that whatever budget was allocated in the last mission quota, that's all used up already, all right? So there is quite a lot of activity around, and that's why we are excited. And as students or somebody who is looking at from the far, why you should be excited about it, right? Because if these industries are going to come, then they need people, and you need an ecosystem around this industry, right? Why we have a very vibrant automobile industry is because from screw pins to gear wheels, we can make it all made perhaps in Pinia. I'm not even calling Karnataka. You can do everything so local that you can look at forecast and then for your own requirement. So this requires a deeper insight. So we need to address the gaps, right? When you look at these gaps, primarily on the skill set that we have, right? So semiconductor technology is very nice. VLSI, we thrive on VLSI design, right? Bangalore is known for that. We have so many design houses that fabricates or rather fabricates all the devices outside. But we design it here. We generate IP here. But the hardware is generated somewhere else. So how to circumvent this? By putting a fab here in India, okay? So then you can have a much more closed loop ecosystem. So there is a good case here, right? But why we need it, right? And for long-term implication as well. So this is going to be a little bit technical talk. So this is just a background of it. And why we need to improve the skill sets, right? Because you have a shortage, right? And that shortage need to be matched, and the only way that you can do it is through engagement with industry, engagement with academia, and so on. So we don't have any problem with the programs that we run at our universities, right? So there is VLSI program, right, and associated electronics programs, semiconductor programs, but they are geared towards design, right? But then how do you translate those programs to something that can offer to a manufacturing industry? So the requirements are a little bit different, right? So why it is different, how that is different is what I just want to share with you today, okay? And the basis of that is this, right? So you see here, this is a processor, i5 processor, Intel processor, it's in the socket, right? And you just clutch in the socket, it starts working once you fire it up, right? But we know, this works as a processor and it has transistors, right? The question is how these things are made. Right? We say, okay, semiconductor fab, they make these processors, but what exactly are they making, right? How are they making, right? So what is the essence of it, right? It's similar to building an infrastructure like this, for example, right? First thing that you do is you survey the land, and then you make foundation, right? Before that, you need to actually have a plan, approve the plan, and then you make foundation, and then you start building on top of each other, right? So there is a process associated with that. So one should know how these things are built, okay? So my idea for the next 50 minutes, or rather 40 minutes or so, is to give you a feel for how these things are made, okay? Or rather the integration that we do in order to make this, okay? And this is actually a cross-section of a chip, okay? So what you see here on the left side is an A5 processor. This is an Apple processor made by Samsung. I particularly picked up because how interconnected this semiconductor technology is, right? Using 45 nanometer technology. So it's Apple and Samsung, right? They are, competing in the market, but Samsung makes their chip, right, on their own. But Apple believes that Samsung can also make their chips, right? But there is no conflict of interest here. It's pure business. It might look like, I mean, how the hell, they keep these two separate, but it works, right? That is the, the mature industry that we have, all right? So the question here is, how do I build this? It looks like a very complex structure, right? And the transistors are sitting at the bottom, right? The transistors, that the bright and the dark small pegs that you see, so those are all isolation lines. The transistor is right at the bottom. And whatever you see till top, it's just connecting them, all right? It's like you have the active region at the bottom, and then you start connecting, wiring these devices is what we do, all right, across all these layers. The question is, how do we build this, okay? And the question is, we need to understand, first of all, what these transistors look like, right? And before we actually get into making of these transistors, we should understand the ecosystem around this integrated circuit, right? So as I mentioned, there is quite a lot of design work we do, okay? And that revolves around this particular block, okay? So there is quite a lot of CAD-based computer-assisted design and modeling that that is done at two different levels, right? So one is at the system architecture and circuit level, right? So system architecture means, am I building a processor? Am I building a memory, right? Am I building an analog based system, or am I building digital based system? So am I building it for the processing industry, or am I building it for communication industry? So the requirements are very different, okay? And it starts from there, the application domain, and breaks down into circuit design, and then comes a much more finer detail, right? So once I draw the circuit, and then these circuits need to be defined using physics models, right? So how they work. And then even going below that, it need to get data from process, right? So when you're simulating, some of you might be from universities or some industry where you do simulation of your designs, structures, right? So it is very easy to design something very ideal. It's very easy, but that's useless, all right, when it comes to practical application. So you need to get the data from what is realizable. That means what you can make in reality, okay? So an architect will bring you a very nice, design that this is how the building is going to be. But then the civil engineer will say, this will not stand, okay? Because structurally, this is very bad. Artistically, it looks nice, but structurally, it's a very bad design, okay? That is the input from the process technology, that what you can make in the fab, right, for real, right? And then associate it with the physics, so you get something that is pragmatic, right? So all this now comes as a single package because the data from the industry can be brought into this simulation tools. So at abstract level, as I mentioned, you start from silicon, which we know is a semiconductor material, devices, complementary metal oxide semiconductor based transistors, and then you can build your abstraction as you go along, okay? So what are we looking at? We are looking at two things. One is the transistor, okay? On the left side, you see this is a very old image from Intel, right? So the thin wires, the bright spot that you see, that's actually the gate, right? So that's one transistor. And then what you see on the right side is actually the copper lines that are connecting the transistors. So these two are the essential ingredient, right, to make any circuit, all right? So how many of you are from electronics background? Nice. So if you look at these structures, right, in reality, this is how they look. But then when you ask any, designers, right, so they are very familiar with what is called schematic. They said, I want to build a circuit, okay? So what they do is, okay, this is the symbol for a transistor. Use this, and this is the functionality that you get, okay? And they start building their circuit based on the functionality. You see, voltage versus current, right? As a function of voltage, the current will change, and that is the idea of a transistor. It's just a switch, Okay, it switches on and off, and we control the current, right? On the left side is the schematic, on the right side is actually the character. So the circuit designer take this and then build their circuit around it. But at the middle is actually the real transistor, right, that we built. Okay, but hardly any designer is bothered about it, particularly circuit designers, right? But as somebody who is, developing this transistor, they should know how these transistors look. All right. So the popular word that you hear, like CMOS circuits, right? So what does that mean? So it means complementary metal oxide semiconductors, right? So it means the N and P, that means the electrons and holes, right? So those are all the fundamental charge particles that we use to control the flow of electrons. So all that you do with electronic circuits is to control the flow of current. And we are controlling it with a switch, and that switch is called a field effect transistor. So there are two transistors here, right? And using the two transistors, which are complement in nature. That's why you say CMOS, right? It's a metal oxide semiconductor junction. But if you take N and P, they are two polarities, right? So they complement each other. And the characteristic that you see on the bottom right is also complementing. And that's the reason why we call this as a complementing metal oxide semiconductor technology. So this is all about semiconductors, right? So the device, the transistors. But then another popular word that you hear whenever you talk about semiconductors is scaling, right? We have to reduce the transistor size. You must have heard the transistor size from 22 nanometer, 14 nanometer, 10 nanometer, 7, 5. They are constantly trying to reduce the size of this transistor. And that is what we call scaling, okay? So how many of you have a feel for, let's say 100 micrometer? So this is a nano conference, right? So we should have a feel for it. Can anyone tell me how large is 100 micrometer? This is very typical. 100 micrometer, give it a shot. Hair strand is what I know that some of you might know. Okay, one should have a feel for the size. All right. So a typical average single hair, right, is about 100 micrometer. Right. So we are talking about transistors that are much smaller, probably about 10,000 times smaller, right, to start with. So it becomes very small. Okay. So that means you need to reduce the size of these transistors. And how do we do that is the question here, okay? And this is the journey of, the transistors from micro to nano era, all right? So about 10 years back, there was a big transition, right, where we call it as a planar transistor. And I will show you a little bit better image there, right, where the transistors were just on the plane surface and the gate was sitting on top, right? But as the time moved on, right, the transistor size is constantly reducing. We started with, 130, 180 nanometer node, and now we are looking at, really tiny transistors, right? So we are looking at 5 nanometer that might go into production, okay? So these are all the sizes of the transistor. I'll show you exactly what that means. But then you look at the architecture of these transistors. They also started to change, okay? So these architectures are primarily to control the charge flow or electron flow, okay? When the size of these transistors were becoming smaller and smaller, you have to apply enough potential to stop the leakage, right? So that is the major problem that we had between the source and the drain. It's between the charges are moving from source to drain, right? And you need to make sure that they don't leak, okay? So that's where you put the gate. The reason why we call that as a gate is it acts as a gate where whenever you want to open the charge, you open and it conducts and then you close it. And this gate has to be really tight, right? And the architecture as we move on started to evolve in order to make sure that the gate is tight so that there is no leakage, okay? So this transistor nodes, this is the typical term that we use, right? What do we mean by transistor node? Okay. So basically the transistor node defined as, the separation, rather the size of the gate basically, right? So you see that orange one at the center, that is the gate, okay? And that gate is avoiding any charge flow between the drain and the source, right? So this is the gate. And the size of this gate used to be called the node, right? But then things evolved, right? And these days you also call half pitch as a node, okay? And the pitch means the contact between the source and the drain, right? So this is what you call it as a pitch. And these days half pitch is also considered as a technology node. So you have to read a little bit carefully. And the reason why it becomes very difficult to define right now is because of the bottom picture that you have, right? So in the past we used to have a very planar transistors, right? You have this doped region where your charge is moving and the gate is controlling, and we started to make these kind of fins, okay? It's called FinFET. And then now we have very complex multi-stack gates, which is called gate all around, right? GAA FET, field effect transistor, but gate is around, right, the transport layer. So in these particular cases, what is node, right? So what is the gate size? It's very difficult to define, all right? So in the past, we used to have something called ITRS, right? So this is a roadmap that was telling the industry and researchers, this is what we need in next, 18 months or next year, okay? And we followed this religiously, and this is what we call Moore's law. How many of you heard of Moore's law? A lot of you, right? So Moore's law primarily predicted that you double the transistor numbers every 18 months or so, right? And associated specifications were also followed, right? But then this particular projection is not valid anymore, right? Because the transistor technology has become so complex, and this whole idea of defining the node, right, itself is gone, right? So now things are defined as functionality, right? So there is no critical dimension or dimension-based or number-based roadmap. It's more on the functionality, which becomes very arbitrary, all right? So this is the basis of making these transistors, right? Why we want to make it smaller, and also, what is the push, towards making it smaller. So now we shall move into ways of looking at this from, making point of view, okay? So the course is about, technology. We are not going to look at the physics behind this, right? So on the left side is what a designer will draw, okay? Basically your architect is that this is what the functionality is going to be. Simple inverter, right? So you have P-type metal oxide semiconductor based transistors and then NMOS transistors, right? Those two are connected in parallel and the bottom one is in series, okay? So very simply connected. But then this is not how we make it. This is how you draw it. How you make it is on the right side, which looks completely different from the circuit, okay? So the layouting is completely different from what a designer would draw, all right? Similar to a difference between an architect and a civil engineer. He makes plans at what level? At the foundation level, plinth level, floor 1, floor 2, column. All these things will look very different from, a larger architect's image, right? So that is what we are looking at, right? And once you have that layout that you have to make, physically make, then we take that layout and start making the circuit, right? The different colors there indicate different layers, right? Like what I mentioned, one is a foundation layer, there is wall, there is column. So these are all different elements. You cannot make them all together. You have to do one by one. Similarly, all those colors that you see, they are of different functionality. So that means I have to do that at different time point, right, on top of each other. And this is what we call a process flow, okay? So we call that as a process flow. and the process flow will have multiple steps, right? Starting from isolation, implantation, gate, silicide, contacts, metals, and so on. So there are a number of processes that you need to do. A typical advanced level process, or rather processor or a memory, would take anywhere between 400, 500 steps. Okay, so that's why they are reasonably expensive. And then we classify these steps based on the functionality. There is something called front end and there is called back end. So the active region that I do, the only making the transistors, that I call front end, okay, where the transistors are made. And then the back end is primarily connecting. All the wiring that I'm going to do, that is called back end. There is something people also define, something called middle of the line, okay, that is just a part of the back end, right? So not really back, but between the back end and the front end, people call something called middle of the line, okay, which doesn't have much more significance. It's good to know that there is one like that, okay. So the philosophy behind this classification is transistors are made at the front end and then the connections are made at the back end, okay. This is philosophically defining it. The other way also we look at it is the front end we can use high temperature processes before the metals come in. When the metals come in, you should not heat up your chip or rather your wafer. Why? Because metals has low melting point and they start to flow, okay, and you will have short. And that's one of the reasons why all your processors are actively cooled. If you don't cool it, the temperature rises above 500 and it's gone, okay. Let's look at how we make these transistors, right? The first thing that you make in any semiconductor or silicon based circuits is to create isolation, because we know it's a semiconductor, right? You're handling charge flow, right? Current flow. The easiest thing to do is to short everything. But what you are doing, you are controlling the flow of electrons, correct? So that means you have to create isolation. They should not all be connected before you start, okay? You create isolations and then you create transistors within this isolation. And that is what we call isolation module, right? And this isolation is provided by the best, the insulator that we can get from silicon, which is silicon dioxide, okay? So silica, right, where you get sand. Sand is nothing but silica, and refined of that is silicon, right? So you can use silicon dioxide, which is a very good insulator. It will not conduct electricity, right? We can use that. And that particular process is called shallow trench isolation process. The way that we do that is we take silicon and then we deposit very thin layer of this silica, all right, by using dry oxidation. That means I heat up the silicon and then pass oxygen. So oxygen likes silicon and they react and they form silicon dioxide. And this silicon dioxide is insulating. But this is not the insulator that we want. It is just to protect the top layer. And then you can come with silicon nitride, which is again a silicon-based material, which is very hard. So some of you who are coming from materials background, you know that silicon nitride is a very hard material, particularly crystalline silicon nitride. If you can do that, it is really, really hard material. Okay, and in this particular case, we deposit this silicon nitride by using CVD technique, which is called chemical vapor deposition. So I put in silane that has silicon, and also I put in nitrous oxide. So they react and they form silicon nitride. Okay, again a very resistant material. And then the next step, what I do is I dig a well, right? So I make a small well to expose the silicon underneath, all right? And the whole purpose of making this is to fill it up with silicon dioxide, right? So there is a liner oxide, that doesn't matter. So you fill in with silicon dioxide using, again CVD technique, okay? Chemical vapor deposition. You throw in the TIOS, right? tetraethyl oxysilene that will react, in the plasma, and then you will get silicon dioxide. And then what we do is we can remove whatever excess material that we don't want, okay? And only silicon dioxide is kept, and this will create an isolation. And this is what we call isolation oxide. Why? Because you can make a transistor on this side and this side, it will not conduct, okay? And some of you might be thinking, okay, there is something beneath this oxide. Will it not conduct below that? Okay, it is possible, but then what we do is we make this top layer highly conducting, and this silicon that is underneath, the conductivity is very low. Okay, so that is how you do it. And this is actually a scanning electron microscope image of how it is made, right? So you can see those trenches, and they are filled with silicon dioxide, and then you can planarize it. Okay, so what you see here is the thing that you get in reality, and you can see here these trenches are very narrow. In this particular case, about 170, 180. This is a 180 nanometer trench that you get, and the regions that are in between, right? You see a cap layer, and that is something that we will use for making the transistors. Okay, and that is what we will do. And in order to make those transistors, we need to have the gate put in, right? And let's look at the gate a little bit more carefully. So now you have made this oxides, no? Both the sides you have made oxides. So the silicon is available, and that is where you are going to conduct, right? Source and drain are going to be placed, and the gate is going to come and sit right on top, right? So this is the gate that is going to come on top, and then the conduction is going to be in this direction, and the gate is going to prevent conduction based on your interest. Okay, and this is the planar technology, and these days we have 3D transistors, FinFETs, Tri-Gates. There are many names, depends on the industry. So this is the fin. So instead of a planar, so you have a very thin fin that's going to conduct, and you are going to control the flow of current by using this gate. All right. So this is pictorially, this is how it looks like. But then in reality, what you see on the bottom right is actually a FinFET transistor, right? So those are all fins. There are multiple transistors connected together. All right. So you can have a single fin or multiple fins. Okay. So now the question is, okay, this is good. So how are we actually making it, right? So we can start with where we left. Okay. So we left here. There is a silicon dioxide that we had here, and then we had this, yellow and purple. It looks like purple here, but two different dope, right? So they are different concentration of dopants. That's going to increase the conductivity, right? So I told you the conductivity can be increased by doping silicon, right? So it's a semiconductor, right? And then we do a cleaning of this, and then after cleaning, you come in with oxide again, right? So it's called, atomic layer deposition or physical vapor deposition of dielectric. And on top of the dielectric, you can put a polysilicon, polycrystalline silicon. Again, silicon is core here. We deposit it using chemical vapor deposition techniques, and then we use lithography. Okay, so lithography is another important patterning technology that we use, where we can make thin lines from a sheet of material. So I take a sheet of material, and then I want to make a thin line. We use a technology called lithography and etching. So if you do that, those red marks that you see here, these are all going to act as gate. Okay. But the question here is, okay, there is a source and drain here, and there is gate sitting here. It is polycrystalline silicon. It is important that the gate should have control over the channel. That means the gate should have very low resistance. Okay, and polycrystalline silicon is not known to have low resistance. It is better we change this polysilicon to a metal. Okay, but the problem here is if I put a metal here, right, at this point of time, I won't be able to survive, without diffusing the metal inside, because the metal will diffuse. into the active region. I want to keep the metal away from my transistor as much as possible. So this particular problem is solved by using called a replacement metal gate. So you can start with the polysilicon gate that I have here, right? And then I deposit oxide, again silicon dioxide, planarize it. I'm just polishing it, and then I can planarize, and then I expose these gates, okay? And then I can remove these gates selectively, right, by using chemical processes, and it will create these kind of small trenches. And then I can fill this trench with metal, right? And then again polish the metal. And if you do that, I have replaced the polysilicon with metal, and this is called replacement metal gate or disposable gate process, okay, which is still used in the advanced CMOS nodes, okay. So now the gate is metal, which I can use. And this is something that either done first or last, okay. It's called gate first or gate last process based on the temperature and the thermal budget, because you have to be very careful about the temperature that your process is going to see, all right. So once you have these gates, then you can think about making your junctions, okay, the source and drain. And that is done by using a technique called implantation, okay. So silicon is a semiconductor, right? So intrinsic silicon is highly resistive. It will not conduct. But then if you dope with boron or phosphorus, the conductivity increases, right? How do you make this boron and phosphorus dope? You implant. You take this boron and shoot it with very high energy, okay? And they will go and implant or go inside the material and stay there, okay? And that is what we call implantation. So you can see here, this is the gate, and then I can shoot the boron, at a certain angle with a certain energy. 15 kiloelectron volts of energy is what we use to throw these atoms onto silicon, and they go and implant into it, and they are sitting there. They will not do anything. What you have done is you have put that dopant inside. They will only be active when you make bond between boron and silicon. When you implant, they are not bonded. They are physically sitting close to each other. It's like going to a party and then there is somebody that you are just smiling at. You haven't started the conversation, right? The conversation will only happen if there is a catalyst. That catalyst here is heat. If you give heat, they react, and now the silicon conductivity is changed, okay? And you can use different energies. You can see here this is 15 kilovolts and this is 5 kilovolts, right? And that will tell you how deep you are going into the silicon, right? If you use less amount of energy, it will stay on the top. If you use very high energy, it will go deep in, okay? So we call that as source drain doping, okay? So once you do that, you start to create this transistor along with this source and drain sitting next to it, okay? So now you actually have a transistor, okay? So you have doped, right? You have changed the conductivity, and you have a gate that can control the conduction between this, and this is all perfect. So you have a transistor now, right? And before you use it, you have to do some annealing. As I said, there is a catalyst, which is temperature. That RTA means rapid thermal anneal. So you are not going to cook your transistor for a really long period of time. There is a heat that is applied for about 1.5 seconds, okay? And the temperature here is going to be about 1050 degrees. So imagine 1050 degrees, let's say 1000 degrees, 1050 is very accurate number. 1000 degrees, 1.5 seconds. How are we doing this? Okay, it's not a furnace. I mean, if you want to bake something, even to achieve 180 degrees, you have to wait for about 10-15 minutes to reach that temperature. Imagine that you have to reach 1000 degrees in 1.5 seconds. How do we do that? It's not your regular heating coil, okay? This is done by using light, okay? Infrared light, very high power infrared light that just flashes, okay? Similar to the light that we have here, right? probably when you go for a buffet, you have this IR lamps. They are basically not for light. They are heating. They are heat sources. Okay, and that kind of lamp with very high power, but that will just flash. Okay, so that is how you heat it. And when you heat it at that much speed, right, rapid thermal, now the transistor is active, right? So all the dopants are done. And once those transistors are done, this is how they look in different kind of generation, right? Going from 90 nanometer node, that means the 90 nanometer is the transistor size here, to 22 nanometer. They essentially look similar, but you can see some contrast there, right? So these contrasts, this is transmission electron microscope. These contrasts are coming from the materials that people use. Okay, though the architecture is similar, different companies will use different material, right? So that is their proprietary, structure, right? So based on that, people use different structure. And once these transistors are done, the next step is connecting them. Okay, so then we go into the border of the contacts, right? So we want to make contacts of this, right? So before we make the contact, something that you may want to know is, once you have this doping done, right? So you just have to connect it, right? So it's like putting two wires together. This is a conductor, this is conductor. If you touch, current will flow, right? As simple as that. But then now I have a transistor which is conducting. I need to connect with the wire, right? I can do that. But the only trouble is, the conductor that I have is a semiconductor. And then the conductor that I want to connect with is a metal. So it becomes a metal to semiconductor contact, which is not very trivial. So that means the resistance for flow of electrons will be high if I don't take care of this junction. Okay, and something else happens, that's what is shown here, which is called parasitics or current crowding. Okay, all the current is going through that small contact. You don't want that, okay, because that becomes a weak point for failure. So what you want is a conducting layer that is flat, where your contacts can come and end, right? So that is called a silicide. Okay, so the silicide is basically an alloy of silicon with a metal. When you make this alloy, then it becomes highly conducting. Okay, so that silicide is formed by very, very simple process. You deposit metal and then you raise the temperature. What happens? I told you metal will diffuse. It will diffuse into silicon and then it will make a silicon metal alloy. The interesting fact here is, the exposed parts are the ones that are doped where you want contacts, right? The source, the drain, and the gate. If you look at all the other parts are with oxide or with silicon nitride, right? So those places, the metal will not diffuse. It's a natural process, what we call self-aligned process. Okay, very low overhead on the cost in doing that. So when you just deposit the metal on top and then you anneal it. So you can see wherever it sees silicon, it goes in and makes a metalloid, and the rest of the places it is still sitting there. So I can remove that by using a wet chemical. Okay, so this is called a self-aligned process, silicidation or salicidation in some cases. So once all of this is done, then I'm going to connect the transistors. Okay, so that is the last module that I have, which is called contact module. Okay, so I have all the transistors done. I'm going to connect, and these connections that I'm talking about is basically lifts and bridges. Okay, so I have something from here, from move there, right, without crossing something. How do? I make a bridge. Okay, so everyone can move on their own, right? So I want to move this bridge. So how do I move? I have to first vertically move up and then horizontally move and vertically go down. Okay, so this vertically going up is called a via or a contact, and the horizontal movements are called metal lines. Okay, so first let's look at this contacts, right? Is basically your transistor is there, and then these metal lines cannot stand in air, right? They have to be concealed in a dielectric medium where there is no conduction. Okay, so the popular material that we know is oxide, silicon dioxide. We deposit silicon dioxide and then planarize it. CMP is chemical mechanical polishing. We planarize it, and then we make holes. We make holes wherever we want to connect, right? Source, drain, and gate, all of these are connected now, right? Or rather opened up now. So how do I connect it? I throw in metal, right? So using chemical vapor deposition process, which will be a tungsten metal. I throw metal on and fill up all of these gaps. And after filling this gap, I still have this metal here, right? I don't want. They're all short now. I have to remove that material. What I do is I polish, right? I can polish it and then I can remove this. So now these are all isolated plugs that I have. And now these plugs can be interconnected. And these plugs can be interconnected by using interconnect modules. I'll tell you how that is again. So we deposit a thin layer of metal, in this particular case aluminum, right, which is done using physical vapor deposition. Just the thin metal is there. And then you can etch the metal. I can remove wherever I don't want. That's called etching, right? And now you can see these two transistors are connected now, okay? Because this is a metal and this is a via, right, or a contact. So I said, vertically moving up, moving to the side, and then you can nicely make this contact. And similarly, I can put again an oxide layer and then connect the gates as well, which I'm not showing it here, right? So I can keep doing this by depositing different type of metals, right? In this particular case, I can put copper, right? So which is again a very popular, highly conducting material, okay? And then I deposit copper and then I can polish it. That will give you, all the contacts there. I can keep doing this, right? But there is a challenge for some of you who are interested. If I make these metal lines on top of each other, putting them all together, right? Then I start to get what is called the parasitics, okay? So this is something that we have studied in basic electrical circuits, that if there are two metal lines very close to each other, you will generate capacitance, parasitic capacitance. Why this is important? Because it is important for your laptops and your gaming system. You want to operate them with high speed, right? So you look at the clock speed, right? 2 gigahertz, 3 gigahertz. Turbo, I want to push it up to 4 gig, 5 gig, right? That all is limited by this parasitics, okay? So the larger the number of transistors are great, but then I need to have so much metal lines in order to connect them. They are going to give you these parasitics, and that will bring down your operating speed, okay? And that is actually a classic delay problem that we have. And there are different solutions people are trying in order to make sure that we can avoid that, okay? At the end, if you keep on doing this building up of all your metal lines, you will end up with such a stack. On the right side, what you see is the top-down image of an i7 processor, which is wire bonded. You see all these pads, and that is where we are connecting those pads to the external world, okay? So that will complete your whole, fabrication of a chip, right? Starting from transistor to complete bond pads, and you have your final product, okay? So I'll stop here, and I can take questions or doubts that you may have. Yes?
How that reliability and accuracy is maintained.
Yeah, okay.
And second question is, you are going to so small now, going to the nanometers. So there is a lot of heat generation in the system. So how this...
So what kind of regeneration you're talking about?
Processor, when we use for a long time, they generate a lot of heat. So how the heat dissipation things are being controlled?
Okay.
So these are two questions.
Okay. The first question is on the process control. You're talking about depositing layers after layers and then you are connecting. how do you control these layers, right? So in the line, what we do is, you see this chip, right? You have this chip, and this is the active region that you see. And within the field, you'll have places for monitoring. Okay, so where there is no transistors, and these regions are to monitor the thicknesses. So we do something called thickness measurement, right, at wafer scale by using optical methods, reflectometry. You can do those measurement to monitor what is the thickness that I have. Okay, so that is for monitoring. But how do you control it? The controlling happens in the process itself, the chemical vapor deposition process I was talking about. You have to tweak your process so that the process is uniform and also repeatable. Okay, so that is process development and process monitoring. That is how we control this. Okay, and the second question is about prolonged usage and the issue with reliability, right? So this is a classic problem, right? But what people do, you can look at the same product. One is more reliable than the other. Where is this reliability comes from? The reliability comes from this whole stack. It's not just the transistors. It's also the metals. It's also the interconnects. Over time, you have a lot of failure mechanisms like metal, migration, right? So electromigration could happen because you are handling very high currents. So you could have electromigration that is resulting in failure. You can also have diffusion of metals to the oxides, and you can have also to the active region. So the conductivity will change over time. So this is all taken care by your process. Okay, what process that you choose in order to do it, and also the interlayers, right? So between two layers, there are defects that you will have, and these defects need to be passivated. There are techniques and technology to passivate these layers by using interlayers. So the choice of those layers, understanding the physics of these defect size, will reduce this reliability problem over time.
Okay. Hello, sir.
Yeah.
Regarding with respect to like threshold voltages, then power dissipation and propagation delay.
Correct.
So with respect to your fabrication of your IC chips, PMOS and NMOS, what are the threshold voltages compared to your millimeter size of transistors?
See, actually the threshold voltage should be kept unchanged. So that's something that the designers, or rather the technology nodes take care of. Okay, so how you do it? It's from the design itself.
Will it be a lesser value compared to your millimeter size of transistors? That's what I'm asking you.
No, so
It will be the same?
I'll show you the scheme, right? This will help you, right? See, there are certain things that need to scale, and there are certain things that should not scale. Okay, so for example, the electric field that you are going to apply through the gate, that should be kept constant, right? So you can ask Saurabh, so he's more of an expert there. If you look at the rest of the parameters, for example, the supply voltage, right, the power dissipation, so all these things scale with node to node, right? Certain things you don't want to scale, okay, because these are all system parameters that should be backward compatible. Okay, so the variations will be there, of course, right, within the process or within the wafer, between the wafers and so on. But certain factors need to be kept, particularly the fields that we are looking at, that should be kept constant despite scaling. That should not scale, and that is the reason we bend our back in the gate technology, right? So you have seen that gate scaling from a simple poly gate to high K and metal gate, and now it's even more complex. There are graded gates now, so it's very crazy, right? So the whole idea of sweating so much in there is to keep that field. Okay, so that's very important.
Thank you.
Good. Yeah.
I'm actually not from this background, but there's one concept that I can't wrap my head around.
Right.
So the whole point of making a transistor from a semiconductor is the fact that we can control the flow of current.
Correct.
So like
So you need a switch to control, right? So you know, the way that you switch these things on and off is this mechanical switch, okay? That mechanical switch is now an electronic switch, which is a transistor. That's what it is. It's, I mean, it operates. What is the purpose of a transistor? It's a switch at the end of the day, correct? It's a mechanical switch, and this is voltage controlled switch. So actually, as an an interesting laboratory demonstration, you can have switches and then play with it, okay? But that's not going to yield anything. But there are ways, where you can have mechanical switches and do something about it. But that's not going to yield what we are, doing with the semiconductor transistors that we are talking about.
Sir, excuse me.
Yeah.
What about the mask layers? How many mask layers you have provided?
No, but we see, it depends on the technology, okay? Probably Saurabh would not, but
For
so
every step, we used to have the single
for
mask
every
layer, right?
every layer there is
Yeah.
mask required, except the silicide layer where we don't need any mask. But it depends on the complexity. So it increases. Technology to technology. Good. All right. Thank you very much. This was post-lunch. I was telling Professor Anil that people might go to sleep, but I haven't seen much sleepy faces. Thank you very much for. I really appreciate.
Sir, is India focusing on spintronic-based semiconductor processing?
We are not looking at any advanced nodes at this point of time, right? So 28 nanometer is what we are looking at this point of time. So things would evolve once we create the ecosystem. But right now, we are not looking at leading edge. It's primarily the bleeding edge is what we are looking at, at least from strategic point of view.
Thank you, sir.
Gentlemen, please put your hands together once again for Professor Shankar Kumar Selvaraj for sharing his insights with us. Professor Anil Kumar, I request you to kindly do the honors. Thank you, sir. We can take a quick 10-minute coffee break and come back. Thank you.
When did you come? I didn't know.